All right, so now we're going to try some practice problems where we're going to not only check for the symmetry of certain polar equations, but we're also going to learn to find their zeros and also find the maximum values of r and also where those occur. But let's start by looking at the symmetry. And in our introduction, we said that we could test for symmetry in a number of different ways. We could actually look to see whether or not our polar equations are symmetric with respect to certain things, whether it's the angle pi over 2 or the polar axis, by replacing r and theta with something else. And what that is depends completely on what we're trying to check for. So I do this by just setting up a quick table. You don't have to do a table. In fact, I don't actually do it all the time. I just did this to try to be a little neater here. But let's go ahead and set up a table and break down what the three things that we're going to be looking for. We're checking to see if it's symmetric with respect to pi over 2, the polar axis, or the pole. So let's start with the angle theta is equal to pi over 2. So in referencing your notes, we know that if a graph is symmetric with respect to pi over 2, it means we can replace r and theta with either negative r and negative theta, or r and the angle pi minus theta, in other words, the supplement. And if by replacing r and theta with either one of these, we should end up with what's called an equivalent equation. And let me be really clear about the equivalent equation. Ideally, our equivalent equation will be exactly the same as our original equation, r is equal to 2 plus 4 sine theta. So if we end up with that, then we're golden. We know that they're equivalent equations. There are going to be times, however, where we don't get that. And if that is the case, we're likely going to have to just use the other check. So if it's not this one, it means it's this one. Hopefully it's both, but if it's not one, it's the other. And what this really saying is there are polar equations that are not the same, meaning they don't look the same, but they actually produce the same polar graphs. And we would still consider those equivalent equations. So what we're looking to find are equivalent equations, and it's hard to tell just by looking at these because we're not really experts on polar graphs yet. So that's why we're going to take a little bit more work to check them algebraically. So let's start with this first one. And hopefully it'll make more sense as I start going through some of these practice problems. So the first equation, r equals 2 plus 4 sine theta, we're going to go ahead and replace the r and that theta with negative r and negative theta, which would give us negative r is equal to 2 plus 4 sine of negative theta. So if I were to just clean this up a little bit here, I'm going to go ahead and divide everything by negative 1. So r is equal to negative 2 minus 4 sine of negative theta. And at this step here, we're going to want to use our even and odd identities. We know that sine of negative theta is equal to negative sine theta because it's an odd function. So we can rewrite this as r is equal to negative 2 minus 4 times negative sine theta. And if I clean that up even further, we can say r is equal to negative 2 plus 4 sine theta. So I'm going to pause here for a second. Compare this to our original equation, r is equal to 2 plus 4 sine theta. We can see here that they're clearly not the same. What we don't know just yet, again, because we haven't worked too much with polar graphs, is whether or not these are equivalent equations. Meaning, do these two equations that we have here, do they produce the same polar graph? And it turns out they actually do. But we wouldn't know that, and we're going to assume that we don't know that. And so right now we're going to say, so far it looks like it doesn't work. That these don't appear to be equivalent equations, even though they are. They don't appear to be equivalent equations because they're not the same. So that leaves us really with no other choice but to check our second option, or second way of seeing whether or not it is symmetric with respect to pi over 2. And that's to replace our angle theta with pi minus theta. So we're going to go ahead and write r is equal to 2 plus 4 sine, and again replace theta this time with pi minus theta. And what we're left with here is the following. R is equal to 2 plus 4, and you might be wondering how to evaluate that. And I'm going to ask you to kind of think all the way back to, you guessed it, sum and difference formulas. So we're going to write this now as the sine of theta sine of pi cosine of theta minus the sine of theta cosine of pi. You remember that? I'm sure you all do. So r is equal to 2 plus 4, and let's go quickly evaluate this. Sine of pi would just be equal to 0, so that first term completely becomes 0. Cosine of pi becomes -1, so -1 times sine of theta, we can just write this as sine theta. And what do you know? We notice here that we do get the same exact equation as what we had originally. So this verifies that we do have an equivalent equation. So we can go ahead and write this. It works there. It doesn't seem like it works there, but it doesn't matter. If one of the two checks work, then we know we can say, therefore, it's symmetric with respect to theta is equal to pi over 2. Okay? And again, if I were to graph both of these two equations, I would see that they produce the same polar graph. So technically they have equivalent equations, but for now, let's just go by checking algebraically and saying, hey, I know that the first check didn't work, but the second test did, therefore it's symmetric with respect to pi over 2. Okay? All right, now let's try the next one, the polar axis. So for the polar axis, remember the two checks here. We can replace r and theta with r and negative theta, or we can also check by writing negative r pi minus theta. So let's check to see if either one of these two work. So let's go back. So for the polar axis, we're going to say replacing theta with negative theta gives us 2 plus 4 sine of negative theta. And this is a quicker check, 2 minus 4 sine theta. And this one clearly does not seem to work. Okay, so let's try the other one. So now for the other one here, we're going to say, all right, let's replace r with negative r. 2 plus 4 sine pi minus theta. And we already did the heavy lifting for 4 sine pi minus negative theta. So we can just write this as negative r is equal to 2. Again, all of this would just come out to plus 4 sine theta. Divide everything by negative r now. R is equal to -2 minus 4 sine theta. In any sense, we see that these are not the same equations. So we can go ahead and just say, therefore, not symmetric with respect to the polar axis. Okay? All right. Now the last check is to go ahead and see if it's symmetric with respect to the pole. So there are two ways for that. We can either replace r theta with negative r positive theta, or we can go ahead and check to see if this works. So by replacing r with negative r, we would get negative r is equal to 2 plus 4 sine theta, which is just r is equal to -2 minus 4 sine theta. Not the same, so this one does not work. Now, replacing theta with pi plus theta. Let's check in on this one. So we would say r is equal to 2 plus 4 sine pi plus theta. So r is equal to 2 plus 4, and then again, we're going to have to use the sum formula for sine, which is just sine pi cosine theta plus sine theta cosine pi. And quick evaluation of this, we see r is equal to 2 plus sine of pi is equal to 0. So again, all of this becomes 0. Cosine of pi is equal to -1. So we would actually have -4 sine theta as our result. And this also is not the same. So we can say, therefore, this is also not symmetric with respect to the pole. And let's write that. Therefore, not symmetric with respect to the pole. So the only symmetry that we were able to verify algebraically was that this polar graph is symmetric with respect to the angle theta is equal to pi over 2. And if I were to go ahead and let's see if I can just go back to that original graph And it looks like I don't have it anymore. But if you recall that graph, it was a limacon. Just look back to your notes from part 1 or just what we did early on in 9.7. It's the very first graph. We see that it is I can just reference it here real quick. Not that, I don't care about reading you right now. There's our limacon. There's our graph, 2 plus 4 sine theta. We see that it is indeed symmetric over pi over 2 and not anything else. Okay, so let's finish up that problem now by actually going ahead and talking about finding the zeros and the maximum values. So let me go ahead and make this a little bit smaller so we have a little bit of space to work with. I can make this a little bit bigger later, but I'll just move this off to the side for now. Okay, so let's go ahead and now let's check for our zeros. So to find the zeros, and again, make sure we're clear about what we're talking about when we're finding the zeros. The zeros of a polar equation are the values of theta where r is equal to 0. Again, the values of theta where r is equal to 0. So it's the theta values where r is equal to 0. So all that means is just like when we found zeros of regular rectangular equations, we're going to set our polar equation equal to 0. So 0 is equal to 2 plus 4 sine theta. Well, just doing some quick solving here, we're going to write this as sine of theta is equal to negative 2/4 or negative 1/2. And just like we did when we solved trigonometric equations, you're asking yourself, okay, what are the angles of theta that give us negative 1/2 here? That give us negative 1/2. So what values of theta give us negative 1/2? Well, theta would have to be equal to 7 pi over 6 and 11 pi over 6. Because we all remember our unit circle, right? All right. So those are our zeros. Those are the values for theta so that r is equal to 0. Now, let's go ahead and find our maximum values for r. So the maximum r values here. Okay, maximum absolute r values. So again, for our polar equation, r is equal to 2 plus 4 sine theta, ask yourself, the maximum value is going to occur when sine of theta is either equal to positive 1 or sine of theta is equal to negative 1. So let's consider both scenarios here. So what would happen when sine of theta is equal to 1? Well, when sine of theta is equal to 1, so r is equal to 2 plus 4 sine theta. If all of this were equal to 1, then r would just simply be equal to 6. When sine of theta is equal to negative 1, r is equal to 2 plus 4 sine theta. If all of this is equal to negative 1, then r is equal to negative 2. But we're looking at the absolute value of r here. So the absolute value of r is equal to 6. The absolute value of r here is equal to positive 2. So which one is the larger value? Well, clearly 6 is greater than 2, so we say that the maximum value of r here is 6. So now we can finish this off by asking ourselves, okay, so since I know the maximum r value is 6, when does that occur? That occurs in this scenario here. The max occurs when sine of theta is equal to 1. Well, to finish this off, we can say our max value of r is equal to 6 when sine of theta was equal to 1, or more succinctly, when theta is equal to pi over 2. And you might be asking yourself, well, couldn't I have just said, I know the maximum occurs when theta is equal to pi over 2 because that's when I know sine of theta is equal to 1? Well, no, not really, because sine of theta could have been equal to negative 1, and we wouldn't have known unless we checked. And sine of theta is equal to negative 1 when theta is equal to 3 pi over 2. So we have to be very clear about only selecting pi over 2 as the angle that produces the maximum. Because we know that if we were to try theta is equal to 3 pi over 2, the absolute value of r there would only be 2, so it wouldn't be the maximum. So just to recap, we went ahead and we tested for the symmetry by looking at its symmetry over pi over 2, the polar axis, and the pole. And we were able to find the zeros and the maximum r values. And in the next video, I'll just do one more problem just to make sure that we